If you've been carrying out your own CFD simulations, then you're probably used to looking at plots of residuals, which looks something like this. Now, there's a lot of confusion around residuals, what they actually mean and how they're actually calculated. Particularly because different CFD manuals often give different explanations, use different notation and use different terminology for residuals and imbalances, and it's not clear exactly what's going on. This is even more difficult when you're trying to assess the convergence of a real CFD case and you're not sure if your CFD simulation is sufficiently converged or if there are any errors and whether those errors are important. Now, what I'm going to be doing for you today is going through a series of talks on residuals in CFD. This is going to be a 4-part series where I'm going to go into detail about residuals, and more specifically I'm going to be providing you with physical understanding so you actually know what residuals really mean when you're looking at them. I'm going to be contrasting that with imbalances, and I'm also going to be looking at things like scaling and normalization of residuals as well, so that you understand the nuances and how different representations of the residual are different and how they vary between different CFD codes. All of this is going to culminate in the final part of the series where I'm going to give you some techniques which will help you assess the convergence of your own CFD cases and really give you a fresh look at how you're assessing your CFD simulations. This is going to be a fantastic set of talks. Let's jump in now with part 1, where we're just going to look at the basic idea of residuals and to understand exactly what it physically means. Now, rather than diving straight into the mathematics behind residuals, what I'm going to be doing is going through an example problem so that we can help develop some understanding of what residuals physically mean first, and then we can go back and look at the mathematics later. Now, the example problem I'm going to be using is simple, straightforward 1D heat conduction in a bar between 2 fixed temperatures on either side. And you can see this in the diagram on the slide. We've got a hot surface held at some fixed temperature, connected to a cold surface, again at another fixed temperature, connected by a 1D bar or rod. And we're dividing that bar or rod up into 4 cells or 4 elements. Of course, we could divide the rod up into as many cells or elements as we wanted, but for this talk and for simplicity, we're just going to use 4 volumes. Now, because those 2 surfaces are at different temperatures, we're going to get heat flowing from the hot surface through to the cold surface, and that's what we're interested in. Now, this is a very simple problem. We're only considering heat conduction, but it's sufficient for us to understand what residuals are and how they're developed. And of course, we can apply that same process to look at other transport equations that are solved by the CFD code. Now, this is a very simple problem, and the solution is actually very straightforward and we can get analytically if we wanted to. If there are no sources of heat in the bar, so we've just got those 2 fixed temperatures on either side, then we'll get the solution, which you can see on the left, and the resulting temperature profile across the bar will be linear, of course. Now, if there are sources of heat in the bar, the temperature profile will be non-linear, and the temperature profile may look something like the image you can see on the right there. And in both cases, we don't actually need to solve this problem numerically. If we wanted to, we could do this with a hand calculation. But for now, it's a very useful example. It's very simple so that we can start understanding what residuals are and where they come from. Now, what we're going to be doing is just setting up a system of equations so we can solve this problem numerically. And then when we've got that, we can start to see where the residuals come in and what they actually mean. And the way we're going to develop the numerical equations is by considering conservation of energy for a single cell in the bar. And if you consider the second cell from the left in the bar, as you can see in the diagram, then for that particular cell, we can have heat conducting out of the left face of the bar, we can have heat conducting out of the right face of the bar, and we could also have a source of heat in that section of the bar from some kind of internal heating mechanism, for example. And if we apply conservation of energy to that cell, we can use Fourier's law to get the heat flux across the left face of the cell and the right face of the cell using the temperature difference across that cell face using the equation you can see there on the slide. And the simplest way to develop an equation for conservation of energy is to start with equation 1. So the heat flux across the left face plus the heat flux across the right face plus the heat source will of course equal 0. And then we can use Fourier's law and substitute in for those the heat flux across the left face and the heat flux across the right face. And you'll notice there that we've assumed that the temperature profile between those two cell centroids is linear. So dt by dx will just be the temperature difference divided by the distance between those cell centroids, delta x. And then we have K and A, and they're the thermal conductivity and the face area of that face of the bar. So that gets us to equation 2. And then the next trick, and what we're going to do, is just rearrange equation 2. And you can go ahead and do this yourself if you want to at home. And we're just going to rearrange it in terms of the unknown temperatures, T1, T2, and T3, where those temperatures are just the temperatures at the centroids of the cells in the bar. And when I'm numbering those left to right, so the first cell is T1, the second cell is T2, that's the one we're currently interested in, then T3, and then T4. So we've got this rearranged equation 3 in terms of those unknown temperatures, T1, T2, and T3. Of course, this is a linear algebraic equation. And what we can do to just simplify this equation for now, equation 4, is we can just take those multipliers in front of T1, T2, and T3 and just write those as coefficients, A1, A21, A22, A23, etc. Just to simplify things and make it easier for us to fit on the slide. But those coefficients, A, just represent those collection of thermal conductivities, areas, and distances, delta x. So now we've written conservation of energy for cell 2 from that previous slide. We could go ahead and do exactly the same process and write conservation of energy equations for the other cells in the mesh. And of course we'd have to do something slightly careful at the boundaries to make sure we got those boundary temperatures in. But generally we'd be able to write 4 equations, equations 6, 7, 8 and 9 you can see there on the slide. And those 4 equations are in terms of 4 unknowns, the unknowns being the temperatures at the centroids of each of those cells in the bar. So you've got T1, T2, T3, and T4. And what the set of equations is physically representing is the heat conduction between those cells in the bar, because of course the heat can only conduct to a cell on either side of our cell. And then that term B on the other side is just going to give heat sources, if there are any, and any boundary conditions affecting that cell in the bar. Now, of course, with 4 equations and 4 unknowns, we can write that quite concisely in matrix form, AT equals B, which you can see there in slide 10. And this is a fantastic position we're in now to get a numerical solution, because we can use a linear algebra solver to solve for the unknown temperature vector. That's T1, T2, T3, and T4, which when we solve the equation will give us the temperature at the centroids of those 4 cells in the bar. And of course, those of you who are used to linear algebra will notice that the length of the temperature vector and the size of the matrices in this case is equal to the number of cells in the mesh. So we've got 4 cells, but if we had 6 cells or 8 cells, for example, our temperature vector would be larger and the size of our matrix problem would go up. But in general, we have 1 equation for each cell centroid in the bar that we're considering. So let's suppose we went ahead and did that, and we filled in our A matrix and our B matrix, and we passed that system of equations over to a linear algebra solver, and we were able to calculate the temperature vector, T1, T2, T3, and T4. And you'll notice in this solution, now that we've plotted it, that the temperature variation between the centroids is linear. And the reason it's linear is when we set up that system of equations and we used Fourier's law, we assumed that the temperature variation between the centroids was linear, so that dt by dx would be the difference in temperature divided by the distance. So we've got this piecewise linear profile between the temperatures in the bar. And of course the end temperatures will be equal to the temperatures of the hot wall and the cold wall. Now, once we've solved the equation and we've calculated that temperature profile in the bar, the next thing we can do is we can actually go back and back calculate the heat fluxes across each of the faces of the cells in that mesh. And the way we would do that is by, once again, using Fourier's law. And in the example you can see here on the slide, for example, if we wanted the heat flux across the right face of that cell, what we would do is we would take the temperature difference across that face and then multiply that by Ka over delta X. And just as a quick reminder, the minus sign is in there, of course, because heat flows in the direction of the negative temperature gradient. So from hot to cold, that's the direction that the heat flows in, which is the reason why you've got that negative sign in there. So we could go ahead and use Fourier's law once again, and we could calculate the heat fluxes across all of the faces in the mesh once we've calculated our temperature profile. So that would be a post-processing operation that we could do to calculate the heat fluxes across the faces. Now, that approach that I just went through there was using a very direct approach, using a single step, passing the system of linear algebraic equations to a solver, which would then, in one step, calculate that temperature profile for us using some kind of solution method, and we'd get that in one overall iteration of the solver. Now, in general, CFD codes use an iterative approach to calculate the solution, where it may take multiple attempts to solve that temperature equation, being coupled or not coupled with the fluid equations, for example, and maybe some other equations of species transport. And so for that reason, because we're using an iterative process to solve this system of equations, it takes us several iterations to calculate that final temperature profile. And what I want you to do is think now of the case where we have that heat conduction in a bar between two fixed temperatures, but with no heat sources in the bar. Now for that case, the final temperature profile will of course be linear between those two temperatures, and you can see that in the plots on the slide given by the dashed line. Now, before we achieve that final solution, of course, with an iterative approach, we calculate a solution that's approximately what we think the temperature profile might be. And until we achieve convergence, that temperature profile will not be the same as the final converged solution. And what you can see here on the slide is that if you were to plot that temperature profile every iteration or every few iterations, you'd find that as you get closer to convergence, the temperature profile approaches that final linear profile, which you of course know is going to be the final solution. And what we're actually interested in when it comes to residuals is not necessarily the final solution, which you can see there in the plot on the right, but what's actually happening in the plots on the left. So we've got a temperature profile, but it's not necessarily the same as the final temperature profile, and there's some error here. That's actually what we're interested in when we're looking at residuals. Now, if we think about these temperature profiles in a bit more detail, what we see is that, of course, the final solution, the temperature profile is linear, and that means the temperature gradient, for this example at least, is constant. So if we looked at the gradient of that slope between each of the points, or between each of the cell centroids, what we would see in the image on the right is that when the solution is fully converged, that gradient will be equal along the line. So the gradient, and therefore the heat flux along that bar, will be equal between all of the cell centroids. Now, before we've converged, we may have some random temperature profile that doesn't necessarily agree with what our final solution is. And if we look at the gradients between those points, we can see that for this example, the gradients don't match. And that's a really interesting observation that will help us to understand residuals. Now, for that case on the left, because the temperature gradient doesn't match on each of the sides of that centroid, that also means that the heat flux doesn't match out of both sides of the cell. So I want you to think back to the cell now, and for this example, we've got no heat sources in the cell, and so that must mean, for us to satisfy conservation of energy, the heat flux out of one side of the cell will be equal to the heat flux coming in from the other side of the cell for energy to be conserved. But for this case on the left, you can see that before we reach convergence of our solution, because that temperature gradient doesn't match, the heat fluxes also don't match. So that means we're not satisfying energy conservation until we have convergence. So the next question is, if we're not satisfying conservation of energy, where does that missing energy go while we're converging? And to answer that question, we need to think back a little bit to what we've actually done to get to this point. And you'll remember that each of the rows of the matrix equation that we set up represents conservation of energy for a particular cell in the mesh. So the second row, for example, represents conservation of energy for the second cell, the third row will represent conservation of energy for the third cell, and so on. And so each of those rows actually represents that full equation for conservation of energy that I have there in the red box, but it was just rearranged a bit in terms of the temperatures. It still represents conservation of energy. So what we need to do is actually go back to that original equation for conservation of energy and add an additional term that captures this missing energy, which we have when we're solving with an iterative process. We've got some missing energy that we need to satisfy conservation of energy. It may be positive if we have an energy under prediction, or it may be negative if we have an energy over prediction. And you can see there in equation 11, I've added this extra term in and called it R, or R2 to be more specific, because this is the missing energy or the residual for cell 2. So now with this additional term, this residual added to conservation of energy, that equation 11 will be satisfied, and we have accounted for all of the energy and we're not missing any. And so what we can see here is that the residual physically represents the local energy imbalance, or the missing energy for a particular cell in the mesh. That's what it physically represents. And of course, we could repeat this process and rewrite our conservation of energy for all the other cells in the mesh. We could rewrite it for cell 3 and cell 1 and cell 4, adding this extra term called R to each of those equations. And this would allow us to arrive at the set of equations you can see there on the slide, 13 through to 16. All we've done is just added an additional term to each of those equations to represent the missing energy, or the energy imbalance. And of course, this set of equations can also be written in matrix form, and that allows us to arrive at equation 17. We've now, rather than having AT equals B, we've now got AT minus B equals R. And that R there is the vector of residuals for all of the residuals in the mesh. Now, of course, we could have arrived at equation 17 slightly differently. If you wanted to use more of a direct approach, you could have just noted that because when we're not converged, AT doesn't equal B, you could just subtract B from both sides, and then the small quantity left over you could assign to the residual vector R. But I prefer to think of things in terms of this derivation, because it allows you to keep a closer grasp on what R actually represents. R is a vector of residual values for all of the cells in the mesh. And this is actually quite a useful equation, AT minus B equals R, because what it allows us to do is, during our iterative solution process, once we've calculated a temperature vector that's not necessarily correct, but we've calculated one, we can substitute that temperature vector into the equation AT minus B, and that will calculate the residual vector for us, R. So this is a very useful thought process for you for what's actually going on when the CFD code is attempting to get an iterative solution. Each iteration, the CFD code will attempt to solve AT equals B and will produce a temperature vector T, which is not necessarily correct. Then what it will do is substitute the current temperature vector that it's just calculated into AT minus B, and that will calculate R, which is the residual in all of the cells in the mesh. And of course, the closer that residual vector R is to 0, the closer we are to achieving our final accurate solution. Because in the limiting case, when the R vector is equal to 0, then we just return to AT equals B, and that temperature vector will satisfy the equation AT equals B exactly. Now at this stage, I wanted to make just a small side point to note that the equation AT minus B equals R, as I've written it here, is in matrix form, but you may also see in some of the CFD manuals, if you decide to look for this equation, you may see it written in discrete form instead. And to understand the discrete form, if you just look at one of the rows of the matrix, for example, let's consider the top row, and if you were to write that out, you would have A11 T1 plus A12 T2, A13 T3 plus A14 T4 minus B1 is equal to R1. And of course, this is just the equation of conservation of energy for cell 1 in the mesh. So it's still that same matrix, it's still that same equation for the residual, but it's just a single equation for the residual in a single cell. So as you can see, some CFD codes prefer to present the residual equation in this way, but both are exactly the same. You could use either equation to evaluate that residual R in a particular cell in the mesh. Now, just to summarize what we've talked about very quickly, and then we'll move on to talk about a bit more, the components of that residual vector R actually physically give you the local energy imbalance in each cell in the mesh. So R1 is the energy balance for cell 1, R2 is the energy imbalance for cell 2, and so on. And you'll also notice that the residual vector R has the same units as the source term B. So in this case, because we're looking at the energy equation and the residual vector represents the energy imbalance, it has the units of watts, units of power, which is the same, of course, as the units of the B vector, and is also the same as the units of AT if you multiply those together. And then the final point for the summary slide, of course, is that when R disappears and when R is equal to 0, then we return back to that original matrix equation which we had previously. Now, I also wanted to mention that throughout this talk I've been framing things in terms of the energy equation, but of course the CFD code goes ahead and solves other transport equations as well. CFD code will solve equations for momentum, so u velocity, v velocity, w velocity. If you have a turbulent flow, it will solve for turbulent kinetic energy, for example, and some scale determining equation. And if you have multi-phase or multi-species flows, you will also be solving other equations for those particular quantities. But for every transport equation that the CFD code is solving for, we will have a matrix equation of the form AT equals B or AU equals B if you have the U momentum equation. And you could follow exactly the same logic that we've done here for the energy equation for these equations as well. And for the U momentum equation, for example, we have this residual vector calculated, but this time the components of the residual vector represent the local force imbalance in each cell in the mesh. So rather than the energy imbalance, it would be the local force imbalance in the x direction for that particular cell in the mesh. And you can see from the same logic that if you solve the V momentum equation, it would be the force imbalance in the y direction, and so on. So for every transport equation solved by the CFD code, we have a different residual which represents the physical quantity being modeled in each particular cell. So cell 2, for example, will have an energy residual, it will have a U momentum residual, a V momentum residual, so it'll have a number of different residuals, and each one of these we can capture it nicely in that residual vector R. Now, because there are a number of different equations being solved, and this will vary depending on what type of simulation you're doing, the majority of CFD manuals often like to group all of this information and knowledge together and just use a general flow variable phi for generality. And it's expected that you, the reader, will understand that phi could represent temperature, velocity, enthalpy, turbulent kinetic energy, or whatever equation you're solving for. And so the general equation is often written A phi minus B is equal to R. But for this talk, I tend to not like using the general variables because often it's easy to lose track of what they physically mean. And I'm just going to be using temperature for my variable phi and only considering the energy equation. But it's worthwhile noting, of course, that what we go through here in this talk for energy, you can, of course, do for any of the other variables, and the approach is exactly the same. Now, the next question is assessing convergence, and how do we do that? Because so far we've got a little grasp that while we're not converged, so before we reach convergence, that we've got this additional energy imbalance in each cell, which is represented by the residual vector. But how do we know and how do we assess when we've actually achieved convergence? Well, the first thing to note is what we saw before, of course, is that if the residual vector is exactly equal to 0, then we have converged universally and we've returned to that original equation. But with iterative solvers on machines that have a finite precision and a finite number of decimal places, the residual vector is never going to be exactly 0. And so that leaves us in a position where we have to use some judgment to determine when is our iterative solution sufficiently converged. Because we'll never get exact convergence with a value of 0. We have to determine when is our simulation sufficiently converged. And actually the problem is even more difficult than that, because if you think every cell in the mesh has its own residual for different quantities, and all of those residuals are going to vary. Now, if we have a mesh with 10 million cells, that means we've got 10 million different energy imbalances throughout our mesh. And at some point we have to decide, is my simulation sufficiently converged or is it not? Because some of those imbalances will be much larger than others. And on the slide here in equation 20, I've just given an example of 3 different residual vectors. And as you can see, for the 4-cell mesh, they all have different values. But how can we determine when the simulation with these vectors is sufficiently converged? Would the first vector be sufficient? Would the second be? Or would we need the third vector if we wanted to deem our simulation to be converged? Now, the first thing which is really important to remember, and is part of the physical understanding of this talk that I hope you get, is that the residual vector itself is a scalar field. So it has a single value in every cell in the mesh, and you can think of this much like you do with other variables like temperature or velocity or pressure. In the same way that you could plot the variation of temperature throughout the domain, you could also plot the variation of the residual vector throughout the domain. And of course, you could then do a contour plot or a line plot or any of your other normal post-processing techniques to observe the values. And I've just given you an example here on the slide of how it might look. For example, if you plotted out the residuals for the energy equation in this 4-cell mesh, as you carried through the iterations, of course, those residuals would change and hopefully reduce, and you could look at them exactly like a contour plot or a line plot. Now, the difficulty here and the subtlety is that while you could do this, if you actually think about it physically, you're not going to stop your CFD simulation after every iteration, output the residual vector, plot it in your post-processor, determine if it's converged, then go back to the CFD code, run another iteration and so on. That's clearly very cumbersome and inefficient, and actually we want a quicker method of determining, is my simulation, does it appear to be sufficiently converged? Can I stop it now and then do some more detailed observations later? How can we do that? We don't really want to be looking at contour plots every single iteration. What we do, instead of looking at the entire field, is we try and get a representative residual that represents the residuals in all of the cells in the mesh. So this is extremely useful if we do it. If we can start with our residual vector, which you can see there on the slide, and then somehow get out a single value that's representative of that entire vector. Because if we can only get out a single value that represents the entire thing, we can plot that value quite easily. So every iteration, we could just get our next representative value out and plot that on a line plot. For example, you can see here on the slide, the image on the right shows the behavior of this representative residual for each iteration in the CFD solution. And this is a lot easier for us to observe and track, and it's a lot quicker to do as well, because we can quickly look at that line and we can see that where the residual is still reducing, for example, if the representative residual is still reducing, it follows that probably the entire residual vector is also probably still reducing, and we're not quite there yet. But then when we get towards the end of that plot, when our representative residual stops changing, then that's an indication to us that our CFD simulation is probably near convergence, or we've now been given a signal that we should go and look at the simulation in more detail and to check, has it converged? So a representative residual is a lot easier to track than the entire vector. But how do we do that? How do we get a representative value for an entire vector? Now, what I'm going to do is just guide you through how you might do this simply and then show you how it's done in practice. If you had a mesh with only 2 cells in it, then your residual vector would only have 2 components. You could call them R1 and R2. And as we know from basic vector algebra, if we've got a vector with 2 components, if we wanted a single representative value, we could just take the vector magnitude. And you can see that there in the plot. That's probably conceptually what I would do and what most people would do at first glance. A vector with 2 components, let's just take the magnitude, and that gets us our representative scalar value. But of course, our residual vector has a lot more than 2 components. It's actually got a component for every single cell in the mesh. So if we've got a 10 million cell mesh, our vector has 10 million components in it. And clearly this formula for the vector magnitude won't work in its current state. We need to do something a little bit more clever if we want a representative residual. Now, it turns out different CFD codes actually use different methods for getting this representative residual, but the idea and the motivation for doing it is exactly the same for all codes. We want a single value that's representative of the residual in all of the cells in the mesh. And these definitions that are used by CFD codes are based on one of the following definitions. They're either based on something called the L1 norm, the L2 norm, or the L infinity norm of a vector. And these are mathematical operations that you can perform on a vector. And all of the CFD codes use a definition that's based on one of these mathematical operations. And what I want to do here today is just quickly breeze through these mathematical operations so that you understand, again, physically what they represent. So then you can go away to the CFD manual or your CFD code and actually work out for yourself what your CFD code is doing. So let's start with the L2 norm first. Now, the L2 norm is sometimes called the Euclidean norm, and it's the easiest to understand. And the reason it's the easiest to understand is it's just the generalized form of the vector magnitude that we thought about a few slides ago. So for the image here on the slide, if you had a mesh with 3 components, for example, you can think of the L2 norm as just taking the magnitude of that particular vector between those 2 points. So we'd have the square root of r1 squared plus r2 squared plus r3 squared, for example. And the important thing to note with this is that if you use the L2 norm, what you're actually doing is providing greater weighting to those cells that have a larger residual. And the way to think about this is just quickly, of course, 0.1 squared is 0.01, but 0.12 squared is 0.0144. So this definition using the L2 norm is going to provide greater weighting towards those cells with large errors in them. So if you had a really good simulation with good convergence, except for 1 or 2 cells, the effect of those 1 or 2 cells on the representative residual is going to be magnified with the L2 norm. Now, if we use the L1 norm, we actually don't have that problem anymore. And this is because the L1 norm actually provides equal weighting to all components of the residual vector. Now, the L1 norm is sometimes called the taxicab norm or the Manhattan norm, and the reason for this is actually a very interesting thing that will help you remember exactly what the L1 norm is. Now, if you think about a block in New York City, for example, or a city that has a regular gridding system for its cars, of course, you would have to follow the straight lines along the blocks and around the city. And this is really what the L1 norm is doing when you think about it. So with this mesh with 3 components, for example, we're going to be walking along the x-axis, then along the y-axis, then along the z-axis, much like we would if we were a taxi cab going around blocks. And mathematically, this is just the summation of the magnitude of each of those vector components. And what you can see here is that if we have 1 or 2 cells with a very large residual, we're still giving equal weighting to those components because we're just taking the magnitude and adding them all up. Now, the L infinity norm is actually the extreme the other way, where all we do is we just take the maximum value of all of the components of that residual vector. So really what we're doing is only looking at the residual from the worst cell in the mesh. And using the same diagram, which I used on the previous slide, you can just see that we're just taking the magnitude of R1 there because R1 has the largest residual in it. And I wanted to just give you a quick little visual example here, just so you can have a better idea of what we're actually doing with these definitions. And I've got that same 4-cell mesh that we looked at the start of the talk for heat conduction in a bar. And this is just 2 examples of how the residual vector might look at a particular point in time. Now, the residual vector on the left, we see those components all have similar magnitudes of around 0.01, whereas the case on the right, we can see that we've got that one cell which has a much larger residual than the others in the vector. This could be because that particular cell in the mesh has poor quality, maybe it's skewed, or maybe for some other physical reason related to the flow field. And with those definitions of the L1, L2 and L infinity norm, we can actually calculate those quantities. And what you see is that from our vector with 4 values in it, we've condensed that down into a single value that's representative of what's going on. And if you just compare left to right, once again you can see that the L1 residual, for example, the L1 norm is larger for the case on the left, because if you sort of added all those components together, stacked them together, that would be larger than the case on the right. But if you took the L infinity norm, then that value would be larger for the case on the right, because we're only looking at that worst case residual there. So you can see that there are different sort of metrics which you could pick, and different CFD codes pick different forms to get this representative residual for themselves. But for us as users, we don't really need to understand why they've picked one metric over the other. We just need to understand the differences so we know which one the CFD code is using. Now, some of you may have noticed that the L1, L2 and L infinity norms aren't sufficient by themselves to get a representative residual, and the reason for that is actually fairly obvious with an example. If we consider this case on the left, where we have a mesh with only 2 cells, and each of those cells has a residual of 0.001 in them, for example, if we then just added an extra cell to that mesh and it gave it exactly the same residual of 0.0010 and evaluate those definitions of the L1, L2 norms, we can see that actually the L1 and the L2 norms increase with their current definition. And the reason for that is we have more cells in the mesh. And this immediately highlights to us that our current definitions probably aren't appropriate, because we don't want our definition to give us a larger representative residual if we have more cells in the mesh. That's clearly not what we want. We want it to be representative of all the cells in the mesh, regardless of how many we have. So we need to adjust our definitions slightly. And the way we do that is that if we're using the L1 norm, for example, we just divide by the length of the vector. And if we're using the L2 norm, we just divide by 1 over the square root of the number of cells in the mesh. And there's no need to do anything for the L infinity norm. And of course, when we have these adjusted definitions like this, you'll very quickly see that the adjusted definition of the L1 norm is just the average of the magnitude of all of the components. So really, we're just averaging all of the residuals in the mesh. It's taking a magnitude and just averaging them and seeing what we get. Whereas the definition based on the L2 norm, once we divide it by 1 over the square root of the number of cells in the mesh, we've actually managed to arrive at the definition of the root mean square. So we've got the root mean square of that vector. That's what we're doing. And the L infinity norm is just the maximum value. So hopefully now, seeing those definitions, you actually have a better idea of what they actually mean and where they come from and how they relate to the residuals themselves. Because when you jump in and look at the CFD manuals, you'll see these kind of definitions all over the place. And now at least you probably have some understanding, and you can start to work out what the CFD codes are actually doing when they're getting a representative residual for the entire mesh. And if I just go back to that example, we can confirm now that if you use any of these modified definitions for these 2 meshes, you can see that actually all of them produce the same representative residual of 0.010, which is a great check actually that our residual definitions are good, because of course if we had a uniform mesh with the same residual everywhere, we would expect our representative residual to also give that value. Now of course, if we have a few cells that have a really bad residual, then the definition based on the L2 norm and the L infinity norm will weight more heavily towards those bad cells in the mesh. And this is the reason why different CFD codes adopt different versions of this formula for the representative residual. So I just wanted to wrap things up for the representative residual, and the key points to take away is that we could actually use any of those metrics if we were writing our own CFD code to get a representative residual for the entire mesh. Any of them are okay. Different CFD codes will choose to use them differently. But at this stage, I also want to mention that what we've got so far is not fully sufficient for assessing the convergence of real CFD cases. And actually what we need to do is we need to take the representative residual that we've just calculated and we need to scale that residual appropriately. And the physical reason for scaling and how we go about doing that, I'm going to cover that in part 2. That's going to be the next one. But for now, it's worth just noting what we've done and where we've reached. We've reached a very nice point. And another thing which also doesn't help and makes this area particularly confusing is that as well as different CFD codes choosing to adopt different norms when they're assessing their representative residual, they also use different scaling factors and different ways of scaling the residual. And I'm also going to cover those in the next talk as well. But hopefully by just stepping through simple steps one at a time and building that understanding so you can follow along with what's really happening, you should be able to navigate and avoid the loss of conclusion. And to summarize the talk as a whole, the key takeaways from part 1 here are that the raw unscaled residual for the energy equation, it physically represents the local energy imbalance in a particular cell in the mesh. And the same logic applies for the momentum equations and the equations for species transport, for example. So the raw residual for the U momentum equation represents the local force imbalance in the x direction in a particular cell in the mesh. And every cell in the mesh therefore has its own residual, and it has a residual for every single transport equation that you solve. And to keep track of all these values and make it easier as a user for us to assess the convergence and track what our simulation is doing, we often calculate a representative residual, and that representative residual, once it's appropriately scaled, is the value that you'll see on those residual plots. When you see the residual plot with all of the lines for the different equations solved, each one of those is a scaled form of the representative residual for the entire mesh. So that wraps up part 1 of my talk on residuals and residual vectors in CFD. Let me know in the comment section, did you find this talk useful and helpful? Do you now feel like you've got a better physical understanding of what residuals are and what they actually mean? I hope you're looking forward to part 2, 3 and 4. We're going to go into more detail and look at scaling and normalization of residuals and imbalances and global imbalances. It's going to be a lot more information. Let me know, are you excited for these talks? Are you excited to finally dispel some of the myths and confusion around residuals? Let me know in the comment section. I really look forward to hearing from you. So until next time, thank you all very much for supporting the channel. I do really appreciate it, and I'll see you in the next video.